Problem 2. A particle S of mass m equals to 0.1 kilograms is connected to one end of a light and inextensible string of length L. The other end is connected to a support O. At equilibrium, the string is vertical and the angle is 0. The particle is shifted to the left by an angle theta 0 from its equilibrium position. The first part. Determine in terms of VA the expression of the mechanical energy of the system S Earth at point A. Whenever they ask about the mechanical energy, directly we should write the expression kinetic plus gravitational potential energy, and the kinetic is given as half mVA squared because the position we are dealing with is A plus mgh but this particle is launched with a velocity VA and it was at a height 1.6. Replacing the mass by its value and the height, we get 0.05 v squared plus 1.6. Part 2. When S passes through the equilibrium position, the speed of S becomes VB equal to 6 meters per second. Deduce the speed of VA. What's the relation between VA and VB? Neglecting the resistive forces, it means mechanical energy is conserved. We should find the difference between mechanical energy between two instants. We should start with the sum of non-conservative forces is 0, then the mechanical energy of the system is conserved. Then mechanical energy at A is equal to the mechanical energy at B. Mechanical energy at B is half mVB squared only because point B is on the gravitational potential energy reference. So if this one is 0, the mechanical energy at B is half mVB squared. VB is 6 squared times the mass, which is 0.1, we get 1.8 joules. Then this value equals to mechanical energy at A, which was 0.05 VA squared plus 1.6. We can find the answer of VA as 2 meters per second. Using the conservation of mechanical energy, verify that the speed of S when it reaches a point m is given by Vm equals to the radical of Vb squared minus 2gl into 1 minus cosine theta. They gave us a hint using the conservation of mechanical energy. Let's state the conservation of mechanical energy between any 2 points. Mechanical energy at m equals to the mechanical energy at B, especially because they mentioned VB. But mechanical energy at B is half mVB squared. And we know that at a given position, the mechanical energy is the sum of kinetic plus potential. But what is mghm? Let's check this figure. In order to find hm, the height of the point m above the gravitational potential energy reference level, let's take this side to study it. OB is L, and it is given. OH is the adjacent to theta, can be found by this right angle triangle. If we subtract OH from L, we can find the opposite of HM, which is equal to it in this rectangle. OH is the adjacent to theta, and we can find it by cosine. So cosine theta is the adjacent over the hypotenuse, and OH is L times cosine theta. Finally, HM is L minus OH, and the answer is L into 1 minus cosine theta. Then mechanical energy can be written as half m Vm squared plus mgl into 1 minus cosine theta. Now, using the conservation of mechanical energy and writing the mechanical energy B equals to mechanical energy at m, we can rearrange this expression to find Vm squared equals to half m Vb squared minus mgl into 1 minus cosine theta multiplied by 2 divided by m. We can find this expression. Square root both sides. This expression is found. Deduce the expression of cosine theta maximum corresponding to the highest position reached by S in terms of L. Remembering that VB, you may use it, equals to 6 meters per second. Whenever they say highest position, directly you should keep in your mind that in the highest position, the speed is 0. the speed of the particle will be 0. Then, using the above expression, that is found in the previous exercise for VB, we can write radical VB squared minus 2GL into 1 minus cosine theta maximum, because M now is considered as the maximum position, and we write it as theta maximum equals to 0 because we said that the maximum position has 0 speed. Now square both sides. VB squared equals to 2GL into 1 minus cosine theta maximum, and try to find cosine theta maximum alone by dividing both sides by 2GL. Finally, cosine theta maximum equals to 1 minus VB squared over 2GL, which is 1 minus 1.8 over L. Determine analytically the speed of S when the kinetic energy of S becomes equal to gravitational potential energy. The mechanical energy in this way equals to 2 kinetic energy, or we can write it as 2 potential energy, because kinetic equals to potential. But we know that at point B, mechanical energy is half m VB squared, which is 1.8 joules, and mechanical energy is conserved, so at any position it is 1.8 joules. So in this situation, kinetic energy can be written as half of the mechanical energy using this relation, and it is 0.9. Kinetic energy is half mv squared. Find V as radical 2 kinetic energy over the mass, and it is 4.2 meters per second. The adjacent document shows the variation of the forms of energy, kinetic, gravitational, and mechanical energy of the system as Earth as function of theta. The first part, match each curve to its corresponding energy and justify your answer. Check this figure. We have 3 curves, A, B, and C. You should start directly with the mechanical energy because it is conserved. Then its curve should be straight line. It is constant at any time. So curve C corresponds to mechanical energy since the mechanical energy of the system is conserved, constant. Then B corresponds to potential energy, gravitational, since the height of S increases with the increase of theta. We still have A, so it is the kinetic energy, but we should specify it. So we say A corresponds to kinetic energy since the speed of S decreases with the increase of theta. Remember that at maximum position, we have maximum angle, but we have 0 speed and 0 kinetic energy. Determining graphically the position of S when the kinetic energy of S becomes equal to the gravitational potential energy. We should determine it even if we have found it before, but this question asks us to determine it graphically. So we go back to the graph and try to find the midpoint of the mechanical energy where the kinetic equals to the potential. Here is the point where the kinetic equals to potential, or even we can consider it as the intersection of the 2 curves. Try to find its coordinates as the energy and its theta. Graphically, we say that the kinetic energy equals to potential energy at theta equals to approximately 57 degrees. Using the expression of V maximum obtained in part 3.1, deduce the length L of the string and the value of theta 0. Remember, VB equals to 6 meters per second. From part 3 to Vm equals to radical VB squared minus 2GL into 1 minus cosine theta. VB is given. It's 6 meters per second. What about point M? Point M is a point at any instance. We can replace it by any position other than B. But we have just known that at kinetic energy equals to potential energy, theta is approximately 57 degrees. If we square both sides, we get this expression, and considering the situation where kinetic energy equals to potential energy, V equals to radical 18 and theta equals to 57, try to solve this equation, then L will be 2 meters approximately. At meantime, L is found. To find theta 0 is the initial angle at position A. we should use VA in this case. At A, the height is L into 1 minus cosine theta 0. How? It is L minus this adjacent, and the adjacent is L cosine theta. HA equals to L into 1 minus cosine theta 0 at point A. Cosine theta 0 then equals to 1 minus HA over L. HA is 1.6, it's given. L, we have just found it to be 2. Replace them and the answer will be finally as 78.46 degrees. Determined by two different methods the value of theta maximum corresponding to the highest position reached by S. First method. From part 3 cosine theta maximum equals to 1 minus 1.8 over L. In this case, L is found, then theta maximum can be found also to be 84.2 degrees. The second method is graphically for kinetic energy equals to 0, theta maximum equals to 84 degrees. This is the end of the second problem. Don't forget to resolve it again.